Today I'm going to talk about the inverse problem in black hole imaging that is based on work done with a collaboration with my supervisor, Enrico Barause, and Sebastian Volkel, also at SISSA. Okay, so let me begin by just explain the motivation for this work. So as you're all aware, gravitational waves have given us in recent years a lot of information about the strong field regime of gravity. However, the Event Horizon Telescope has also produced images from the supermassive black hole M87 that may also allow us to test gravity. The measurements by the Event Horizon Telescope are complementary to those of gravitational wave interferometers, in the sense that the EHT explores objects that are that have a mass of about 1 million solar masses or 1 billion solar masses, whereas LIGO, for example, probes compact binaries that have tens of solar masses. So hopefully, with all this information, this will allow us to test the Kerr hypothesis. That is, that we believe that black holes that exist in real life are described by the Kerr metric of general relativity. These black hole images contain a lot of information about the surrounding space-time and also about the matter distribution in an accretion disk, for instance. In this work, we're trying to tackle the question of whether we can extract the information about the metric and the astrophysics from these types of images. And by astrophysics, I mean the matter distributions. So these images are complicated objects. So, and this is a hot topic. So several authors have tried to simplify the analysis as a first step by trying to constrain gravity using, let's say, generic features of black hole images. And this section, let me call it tests using the shadow size. Essentially, the black hole shadow, in a few words, is the collection of the captured photon trajectories by the black hole. The shadow radius is related to the projection of a location in space-time called the photon ring, at least for a non-spinning black hole. And the photon ring describes the location where photons can follow unstable circular orbits. It is related to a feature in the black hole image that is a bright ring surrounding a darker region in the picture. So the first type of tests one can do with the shadow size is, let me call them theory-specific tests. And essentially the idea is that one can use a known solution to a given theory of gravity, compute the prediction for the black hole shadow, and then compare, let's say, with the EHT measurements in the hope of constraining the coupling constants or the charges that describe this space-time. However, as many people are aware, there are many theories of modified gravity that make this a tedious job. So a more organized way of constraining gravity would be to use, let's say, the second class here that I call parameterized tests of gravity. The idea here is to describe the metric as, let's say, a sum of terms. For example, it could be a sum of 1 over r terms to some power, as in a post-Newtonian expansion, or let's say a Padea summation, a summation with Padea approximants. And again, the idea is to compute the prediction for the shadow size and hopefully constrain the parameters describing the metric. However, when there are many parameters to play, like both of these types of work, one of the conclusions that they have arrived to is that when you have many parameters, the shadow size allows you only to constrain at most some regions of parameter space or some combinations of the parameters. So let me give you an overview of what we're trying to improve in this work. So to begin with, the forward problem is that of computing a black hole image from a known metric and a known matter profile. And this has been studied extensively since the 70s. In this project, we're trying to solve the inverse problem. And that is, we want to start from a black hole image, and from this information, try to reconstruct or recover what the matter and the metric functions were that produce this image. Again, this type of problem has been tackled before by these authors, for example. But the innovation here is that what we want to do is to assume as little as possible about the possible deviations from general relativity. So essentially, the idea is to write the metric functions as a sum of a background term that could be general relativity, plus some possible deviations, arbitrary deviations, that we can describe by some means of some basis functions. And for these basis functions, there are many options. For instance, one can take Gaussian functions. So once we describe the metric with this, let's say, parameterization, we can couple this to a code that produces a black hole image and start doing parameter estimation. And we couple our estimates with a technique called principal component analysis to try to recover the metric and the matter distributions. In general, this is a very complicated problem since the astrophysics has many parameters, and also gravity could have many parameters like spin. But in this work, since this is a proof of principle that this type of approach works, we make many simplifications, and essentially we work with a toy model in spherical symmetry. So just to say a little bit more about what it means to compute the black hole image, once you know the matter content, once you know the metric distribution, for example, that it is a Schwarzchild black hole, once you know you have solved the matter equations, you know the properties of matter, the accretion flow, the only thing left to do to compute a black hole image is to integrate two sets of equations from the source to the observer. I mean, the first set of equations concerns the trajectories that photons follow from the source to the observer. And the second set of equations are called the radiative transfer equations. And these essentially transport the information about the synchrotron radiation emitted by electrons in the accretion disk to what the camera measures as an intensity, integrated intensity. Once we know how to compute black hole images, we can describe a model for deviations of a black hole image produced by GR, simply by taking, again, the expansions of the metric that I described before in terms of background and some arbitrary summations. We can also describe the matter in a similar way, and we can solve the geodesic and radiative transfer equations to produce the modifications of a black hole image. For simplicity, again, since we work in a proof of principle type of project, we linearize the equations of motion to produce a linear model for the black hole image. Once we have described the possible deviations of the black hole image, we can begin to do a parameter estimation. So essentially, the posterior probability of the parameters given an observation given by Bayes' theorem is given by the product of the likelihood of a model to reproduce the image times the probability distribution that describes the prior information that we know about the parameters. For simplicity, we assume a Gaussian likelihood in the intensity for our model. And also we assume that the priors for the parameters alpha are Gaussian. And yeah, the reconstructed metric and emissivity will be given by the maximum of this probability distribution, or actually an estimate for the reconstructed parameters. The errors of this estimate will be encoded in the so-called Fisher matrix, which the definition is here, but essentially will be the Hessian of the chi-square of this likelihood function. Yeah, so now that we have an estimate for the reconstructed metric and the emissivity, we can further clean this reconstruction by employing a technique called the principal component analysis. Essentially what it does is that from our estimate for the parameters, it keeps only the most reliable features describing them. That is, one can use the eigenvectors of the Fisher matrix to identify those combinations of parameters that have uncorrelated errors, and keep only those combinations of parameters that have a coefficient in front that is not consistent with some statistical error, that is not consistent with 0 with respect to some statistical error. This technique, the principal component analysis, has been applied before to describe the shadow edge by these authors. But in this work, we're trying to describe the whole image, that is the whole intensity profile. So as an application, let me show you some of our preliminary results. So with this type of approach that I've just described, here I want to show how we can recover the metric and the emissivity from a mock observation of, let's say, with a toy model for the EHT. So in this first plot, what you can see in gray with the error bars is a mock observation. Here I plot the intensity versus the radial intensity profile versus the impact parameter, as the observer would see in its black hole camera, produced with a modified gravity metric described in this way. So in this metric, I am only modifying the GTT components. And this modified gravity consists of a Schwarzchild part plus some deformations described by a Gaussian bump and a power law-like term. And you can see the comparison of this radial intensity profile with what would be the image of a Schwarzchild metric in blue here. In the right upper panel, what you can see is the same information for the linear model or the mock observation in the left, but in terms of a density plot. And this looks, yeah, well, this looks more like a black hole image. And now we apply the approach that we've described. And here I show you some of the results of how we can reconstruct both the metric functions and the emissivity functions. So let's concentrate first on the lower left panel. In the blue contours, what you can see is what happens if we restrict if we restrict our analysis to the emissivity function only. That is, I fix to begin with the metric functions, and I attempt as a start to describe only the emissivity. So I describe my emissivity function in terms of a Gaussian basis, and with this mock observation, I can reconstruct this blue contour. And as you can see, it follows the injection, which is described by a gray dashed line. We can play a similar game with a metric function. So now in the lower right panel, which you can see in the blue contours again, is the results of the metric reconstruction, assuming that the emissivity function is fixed. And as you can see, we can recover the modification of the GTT metric function in vertical axis with respect to radius. That is described by this, again, this gray dashed line. And finally, we can try to reconstruct both of these metric functions, both of these functions at the same time. However, describing both functions at the same time is a more difficult problem and is more prone to degeneracies. So in our work, we find that it is necessary to include additional information, or that is to enhance our priors. So what we do is that we constrain the emissivity model to be described only by a power law coefficient and an exponent. So what you can see in the orange contours are the joint reconstruction of both the emissivity and the metric. Again, when we assume that the emissivity is constrained to be a power law. So let me conclude because I think I'm out of time. So in this work, we're trying to include more information than the shadow radius by including the whole image and trying to solve the inverse problem that I just described. And we have found that we can recover both the metric and the matter emissivity when considered separately. And we need further assumptions to be able to reconstruct both of these together. Of course, as I mentioned at the beginning, we had to make many simplifications because this is a complex problem. And we only wanted to see as a proof of principle whether this type of approach would work. So as future work, one can extend our approach by including more parameters, describing a more realistic matter flow. And we can also include black hole spin, etc. We can also drop the assumption about the linearization of the two sets of the geodesic and the radiative transfer equations and compute all of our images with a and do the parameter estimation with a macro chain Monte Carlo. However, this is more computationally expensive. Well, thank you.
Thank you very much. Guillermo, are there any questions?
So I wonder how unique this problem really is, because you showed one example which was rather simple. But for example, we know that the size of this black hole shadow of this ring is pretty independent of black hole spin. And then it may be like if the set a spectrum with X-ray satellite, we use response metrics. But it is difficult, impossible to make the inverse of this response metrics. So I wonder what can be the outcome. So how unique this problem is, whether you really are able to make the inverse problem to work and get the metric spin just.
Okay. Yeah, indeed, it's true. As you say, like when we have a black hole, the spin deforms only the circularity of the shadow rather mildly. Yes, but I mean, yes, and there are a lot of uncertainties on the astrophysics side as well. Yes, okay, I would just try to raise again a point I tried to make, which is that when you use only the shadow radius or the bright ring in the black hole image, since, as you say, this black shadow edge is rather circular, this doesn't constrain much. This leaves a big room of parameter space unconstrained. However, what we tried to improve with this was to include more information by including all aspects of the image. Like, yeah, of course they relate to each other in a complicated manner, but yeah, we hope as I tried to show in this example, that this gives just a little bit more of information than just the shadow size. So
Thank you.
I'm sorry, I didn't hear all of your question because the sound is a bit bad. But
thank you, Guillermo. Let's see if there are any other questions. Well, if not, I have a question for you.
Yes.
Can you hear me well? Yes. So my question is about your Bayesian analysis. And where do you consider Gaussian priors? And where do you put like the peak of the Gaussian? And why not flat priors? That would be more like agnostic.
Why not flat? Okay, that's an important point. Okay, let me go to this slide. Okay, so I made a few simplifications. First of all, the HT observes some quantities called the visibilities, not really the intensity in the black hole camera. So we assume a Gaussian likelihood in terms of the intensity. A more realistic approach would use these other quantities called the visibilities. And as you say, yeah, maybe an agnostic prior on the parameters would be flat. However, it goes along the same lines that I tried to describe. That is a more complicated problem to describe both metric functions at the same time. This type of inverse problem is plagued with degeneracies. So you need to aid the reconstruction in some way. So by taking Gaussian priors around 0 for the parameters, that is, we expect that the deviations from general relativity are small. We help this parameter estimation scheme to converge to let's say to a solution. But yes, yeah, we are using more information than flat priors. I don't know if this answers a bit.
Let's stop. Thank you, Guillermo.
Okay.